So, how do we determine if a group bound to a benzene ring is electron donating or electron withdrawing? Well, actually, it's pretty straightforward, and you would think it would have something to do with like the electronegativity. Not really. What it scales with more is the lone pairs. Now, the strength of the electron donating or withdrawing features is going to be more of a function of the electronegativity atom involved. But if we're speaking in a very general sense, any atom bound to a benzene ring that contains a lone pair is in general going to be electron donating. So this is going to make it an OrthoPara Director. So even something like oxygen. Because of these two lone pairs sitting on this oxygen, we end up creating a resonance structure. And this resonance structure is going to stabilize the lone pairs being on these OrthoPara positions. Even though oxygen is more electron withdrawing than carbon, it still, in principle, makes these positions more desirable because they're more likely to stabilize. The ones that are considered electron withdrawing, or groups which are meta-directors, are typically ones that lack a lone pair. So let's say we go with, oh, that was a terrible way to draw benzene. Let's say we draw benzaldehyde. Well, in this case, carbon is equally electronegative with carbon, but because carbon doesn't have a lone pair, it can't participate in the resonance structures. So this would actually make it an electron withdrawing group. Now, in general, you would just look this up. In particular with my exams, there are tables listing what the electron donating and electron withdrawing groups are. But because of these tables, one, more just be familiar with what you would expect based on lone pairs. If you see a lone pair, odds are it's an OrthoPara Director. If you don't see a lone pair, odds are it's a meta-director. So there is one little contentious debate about this. And I say contentious because in preparing for this course, I looked up a whole bunch of tables. Francis says one thing. Francis and Carey says one thing. Other tables and other organic books say other things. And these are halogens. So let's say we have chlorine up here. Is this a OrthoPara Director or is it a meta-director? Well, it's debatable, which is a weird thing to say. Now, I told you before, if it has lone pairs, it stabilizes, and this is what some books contend, is that these are actually OrthoPara Directors because of the lone pairs. They stabilize the resonance structure to make that site, OrthoPara positions, more electronically attractive. But other books will sit back and say that because these are halogens, they're actually more electronegative than carbon, and then they draw the electron density away from the ring, and because of that, they are actually deactivating. So they are actually meta-directors. How do you resolve this? Well, the honest answer is in how they are defined. There are strongly electron donating and strongly electron withdrawing groups, or strong OrthoPara Directors or strong meta-directors. We would classify the halogens as weak directors. So even if you have a halogen, it's not likely that it's really dictating where things are going in terms of the ortho-meta position. So I think this is part of the reason why we had the debate. On one hand, people look at it in terms of electron density. If you have an electronegative element, it pulls electron density away from the ring, which makes it electron withdrawing, which makes it a meta-director, which is why this would be considered weakly deactivating. But then you have the other camp that says, well, really, it's the resonance structure with the lone pairs, and since it has lone pairs, it should be activating. Generally, what we're going to fall to with halogenation reactions is actually a sterics argument. I would argue, and again, this is up for debate, other books will claim otherwise, this is actually an OrthoPara Director with emphasis given to the para position. So, why do I say this? Twofold. One, it's weak. And so even if it were to have an effect, we're not talking like a 90% yield to para. We're talking like it's slightly better than random 1 in 3 odds of where it's going to end up. The second reason I would argue it, and this is something that your books tend to omit in their discussion, even if we have an OrthoPara Director, the reality is they're still going to favor the para position. The reason they're going to favor the para position is steric effects. This is a big group hanging off. So even though the ortho positions are favorable for bonding in terms of the electron density, It's the para position that's the most accessible and most likely to react. I would say if chlorine is going to straddle the line between activating and deactivating, most likely what you're going to produce is the para position for the same reason. This is the furthest away from the chlorine. It is the most sterically accessible, and so that's what's going to happen. So again, big picture. Is something an OrthoPara director or a meta-director? If it's a lone pair, odds are it's an OrthoPara director. If it doesn't have a lone pair on it, it's probably a meta-director, particularly if whatever is bound to the ring without the lone pair is bound to things that are very electronegative. Again, we do kind of have a point of contention with the halogens, but this is more or less how we're going to set our framework for predicting where reactions go.